Ready
to go?
Yep.
Okay. Welcome everyone to this week's CDAR seminar. I'm Lisa Goldberg, one of CDAR's co-directors, and it's my pleasure to introduce CDAR's other co-director, Bob Anderson, who is going to be talking to us about general equilibrium theory for climate change.
Great. Thanks, Lisa. So this is joint work with Kevin Duanmu, who was a postdoc here for about 3 years, ending just before the pandemic, and is now at Harvard Institute of Technology. And it's also part of a larger project concerning externalities in production economies. So we have a 4-author paper and then bifurcated this one into a 2-author paper. So what are we trying to do in this paper? Well, we're trying to take the two main mechanisms that are used for controlling CO2 emissions, namely quota on the emissions. So this is called cap and trade, and imposing a tax on carbon emissions. We're going to focus on CO2 emissions in terms of the wording we use, but much of this is applicable to other types of pollutants as well. So these are well established. Carbon taxes and cap and trade are in force in various countries or subdivisions of countries. So they're actually being used. But in fact, they haven't been studied in general equilibrium theory. So when I talk about general equilibrium theory, I mean the theory that was developed from the 50s, through the 70s and 80s, particularly going back to the Arrow-Debreu theorem of 1954, which is the kind of benchmark model for perfect competition in a production economy. And we want to try to incorporate these controls on pollution into that setting. So as I go, I'll explain why they aren't currently embedded in that setting and how we managed to do that. And we're going to introduce two models. So the quota equilibrium model is very much related to cap and trade, but what we do is actually more general than cap and trade. So we'll see how it generalizes the notion of cap and trade, and also a tax equilibrium model. And then we're going to look, first of all, we're going to prove that equilibrium exists in the quota equilibrium model. We're not going to show that equilibrium exists in the tax model, because in fact it doesn't always. And we'll give an example where existence of equilibrium fails. And this is something we want to develop further. We want to get a better understanding of when we know that there will be equilibrium existence in the tax model, but I'm going to show you that there's an issue here. And indeed, that's one of the motivations for why we're bothering to embed these notions into general equilibrium theory. The reaction might have been, well, of course, there's an equilibrium. You just impose this and then use the general mechanisms, in the Arrow-Debreu and subsequent models, and there will be an equilibrium. And the answer is, well, no, there isn't. So the existence of equilibrium becomes a non-routine question precisely because it, in fact, doesn't always exist. Second thing is the welfare property of quota equilibrium. So in a sense, this goes back to Adam Smith 250 years ago in The Invisible Hand. It was made explicit in the 1950s in the first welfare theorem. It says that if you have an Arrow-Debreu equilibrium or a Walrasian equilibrium as a closely related term, then it's Pareto Optimal. That's in the absence of externalities. And of course, here, when we're talking about climate change, we have a big externality that what happens elsewhere in the economy in terms of production or other people's consumption affects my preferences. But in the Arrow-Debreu model, there are no such externalities. My welfare depends only on my own consumption, and equilibrium is Pareto Optimal. There's no way of making everybody better off than at the equilibrium allocation. Okay, so we have externalities, and in fact, we would expect to see no welfare properties, but in fact, we'll show that the quota equilibrium is constrained Pareto optimal in a particular sense that I think is pretty natural and has implications for policy discussions about regulation of pollutants in general and CO2 in particular. Yeah.
Well, you opened.
Yes, sure. Yep.
Secondly, for those of us who don't have a strong background in economics, can you just say a few words about each of those kinds of equilibriums and why we need several?
Well, okay, so the essence of general equilibrium is supply equals demand. So we assume that individuals maximize their preferences given the prices prevailing in the market as given, and that firms choose their production in order to maximize profit, taking the prices prevailing as given. And then an equilibrium is a set of prices and the associated consumption decisions by consumers and production decisions by firms, so that supply equals demand. And that's the case with Walrasian equilibrium, air-debris equilibrium, various other formulations. Now, when we look at the two notions we introduce here, we need to be clear about what the notion of equilibrium is, and we will do that. It's again a supply equals demand story, but with a constraint, a quota built in or a tax built in.
A quick question.
Yeah.
It would seem that a quota is just a special case of a tax where the tax is zero up until the quota and then is very high or theoretically infinite above the quota. So if we see a discrepancy in equilibrium behavior between taxes and quotas, that should occur at some transition from a conventional tax to this limiting tax that is really a quota.
So that's a good intuition, and in fact, it's one that many people have had. It's in a book by Bill Nordhaus that is probably the most cited thing for his Nobel Prize, and in one sense, it's wrong.
Well, I specialize in reinventing the wheel.
In one sense, it's wrong, but it's also correct in another sense, and we'll explore that.
Okay.
Yeah, so I think the general feeling has been that anything you can do with quotas, you can do with taxes and vice versa. And we'll show that that's largely true, but that some care is needed in it. So that's the first thing. Rather than sort of arguing informally, yeah, that ought to be right. Basically, we've got a theorem that makes that precise and also tells you what the limits of that are.
Great, thank you.
Okay, so let's first of all talk about how supply equals demand is formalized in general equilibrium theory. So there are actually two versions of this. So the one that supply equals demand, it's the second bullet here. Supply equals demand. This is called a non-free disposal equilibrium. So that's a common term in the literature from the 50s through the 70s, 80s, 90s. But there are issues with that because there are some things for which supply exceeds demand. So an example is water in the ocean. So we're not anywhere close to using up the water in the ocean. And so if we incorporate that as a commodity into our model, then insisting that supply equals demand is going to be a big problem. So for a long time, people have looked at the notion of a free disposal equilibrium where the demand for each commodity is less than or equal to the supply, but there might be some commodities where the demand is strictly less than the supply, and then the rest is left unused. And that's really a very natural formulation in a setting where commodities are either useful or may be satiated. So in other words, it may be that water is really good, but after some point it becomes not helpful to have anymore. That's called satiation, and free disposal equilibrium works very well in settings of satiation, but it works badly when you have goods that are actually harmful, commodities that are actually harmful. I'll try to, so the terminology has typically been to use commodities and goods as being meaning the same thing, but we're going to try to avoid saying that a commodity is anything like CO2 or food or shelter, which might be good or bad. And I'm going to try to distinguish between goods, which are commodities that generate positive utility, and bads that are commodities that do harmful things. So free disposal equilibrium, it doesn't work well in terms of regulation of pollution, because it says that anything that's produced can just be disposed freely. Okay, and in fact, if your goal as a society or government or whatever is to reduce pollution, then you can't do that if people have the right to just dispose of it freely. You have to put some constraints on the disposal, whether that's through some kind of quota or a tax. So free disposal equilibrium cannot address this. Now, what you might be inclined to do is look at non-free disposal equilibrium, which requires that everything be accounted for and exactly used up. The problem with that is that if we really require non-free disposal equilibrium, and pollution is not actually consumed, it goes out in the air and it stays out in the air. It's not. No one's taking the responsibility to eliminate it or render it harmless. Then if you wanted to insist that there's no pollution released into the atmosphere, the only thing to do in the short term would be basically to shut down the economy and go to a pre-industrial society. So that's not a good option either. We need something in between. Eventually, in 2050 or 2100, we might be in a zero carbon environment, but we can't get there today or next year. So we need something in between, which is what carbon tax and cap and trade are designed to do. So we need a feasibility constraint that's different from the ones that are used in general equilibrium. And we do that by defining a quota compliance region. So this is, first of all, we're talking in the context of a quota equilibrium, but we'll see that this region notion also appears in the formulation of a tax. So there are L commodities, and the society wishes to regulate the first K of them. So for most of the story, it would be K equals 1 CO2, but the model will accommodate any number of goods that are to be regulated, and then there are other goods that are not going to be regulated. Okay, and there's going to be a quota on the emissions of these regulated commodities. So if I say that I'm going to allow 1 gigaton of CO2 to be released each year, then my quota for CO2 is 1 gigaton, and this M, it's going to define the compliance region, will be minus 1 gigaton. Okay, so M is the negative of the quota for the first K commodities. This is a vector, and we'll see why it's helpful to have these things be negative. And then we're going to define a quota compliance region. That's this Z of M. And this is a product. So in the first K commodities, we just put this vector M that represents the negative of the quotas. And then for the other commodities, we allow either non-free disposal, supply equals demand, or allow free disposal on a commodity by commodity basis. So in setting up the model, there are some things we're going to regulate. There are others where we're going to insist that supply equals demand, and still others where we're going to allow the possibility that supply exceeds demand. Okay, so what's a production economy with quota? So this is set up in a formal mathematical definition, which is in the spirit of general equilibrium theory, but I'm going to talk about this mostly in words. So we've got a large tuple that describes the various aspects of the economy. And I'm going to say what each of them is. So I need to define all of the terms up in the description of the economy. So the first thing is I need a set of prices. So delta is a set of prices. And so I need a price for each commodity. So there are L components in this vector. And they need to be normalized in some way. So if I multiply all prices by 2, in general equilibrium, nothing changes. My income doubles, but the price of buying each commodity doubles. And so the set of things that are affordable, my budget set doesn't change, my demand doesn't change. But one departure from at least the most standard versions of the Berkeley model is we allow prices to be negative. So, I mean, that is by itself is not new. That's been looked at in a number of papers. However, in the bulk, I'd say 80% of the work in general equilibrium prices are restricted to be non-negative. And you can do that because there's an assumption that there are no bads. Okay, so if there are only things that are either positively desirable or at least harmless, then you can make things work with non-negative prices. But if you're going to have bads that need to be controlled through the price system, then you need to allow negative prices. Okay, so there's a finite set of agents. And
Question.
Yeah.
The prices are probably going to be negative on those first K things, right? Presumably.
Well, presumably, yes, although that's not part of the definition. Is that going to be always true? I mean, yes, roughly that's the idea, yes.
Seems natural, but
Yeah.
will prices maybe be negative? I assume you have the bads in the first K and maybe the goods in the next bunch. Or can prices be negative also on something that
They
want?
So they could. So there could be bads that we chose not to regulate.
Those are bads, and so those could have any price.
Right. So for example, well,
You mean like
well, in principle, whether at equilibrium, they could have a positive price. I don't think so, but I want to be careful about statements like that. So I mean, there are lots of examples of bads that are not regulated. So if you look back not so long ago, CO2 was not regulated. If you look back before 1970, the discharge of all sorts of toxic stuff into water was unregulated. So there's a choice society makes about both which commodities to regulate and how severely to regulate them. And there are likely at any given time to be some bads that are not regulated, either because we haven't realized that they're bad or there's ferocious lobbying in favor of not controlling them or so on and so forth. But the decision about which commodities to regulate is essentially a political decision. And all we can do in this paper is, in a sense, help the political process understand what its options are and hopefully make better decisions than it would in the absence of insight from economics.
So what about something like one of these new age PFAS chemicals that make our Teflon not stick and our
Yep.
Gore-Tex
Yep.
repel rain, and yet when you dump them in the river, they cause birth defects to anyone who's
Right.
exposed to that. So is that a bad or a good?
That's
I mean,
well,
regulated, but it
yeah.
still has value.
well, so the right way to look at that, I think, is you're actually producing two commodities as joint products. So you're producing the non-sticky pan, and you're also producing a chemical which in the residual gets into people's bloodstream and water and so forth, and does bad things. So the way we think about electricity generation in this paper is we burn coal, let's say, and we produce electricity, which is good, and CO2, which is a bad, and those are joint products that you produce together. And I think that's the right way to think about
There's like
that
PFAS
example.
1 and PFAS 2.
Yeah.
But we can't just put a cap on it. What we have to do is control and sort of contain it a lot, and maybe.
Well, you can't. I mean, you can forbid it. So there are all sorts of chemicals that used to be used in air conditioning that are illegal to use now because of environmental effects.
No, I should read on.
Yeah.
Seems
Okay, so we have a finite set of agents, and we need to specify what their consumption set is. For most purposes, this can just be the non-negative orthant. So, well, I don't say that. That's actually going to matter a little bit. In most of general equilibrium, this is just assumed to be the non-negative orthant. So you can consume a non-negative amount of any commodity. Okay, and then there are a finite set of firms, and one of them is special. So we've got J firms that look just like a firm in general equilibrium. It has a production technology, it maximizes profit, so on and so forth. And then we introduce one new firm, Zero, which is the government firm, and it looks like a dummy. Okay, its production set is 0, which means it's only capable of taking 0 inputs and producing 0 outputs from that. Okay, it can't do anything. But it's going to matter, and we'll see why. Okay, and then we've got production sets which are not 0, not dummies from the other firms. Okay, this is just notation. An allocation that's curly A is just an assignment of consumptions to each of the consumers. Okay, now we have to specify formally what the preferences are of agents. So you might think of the agent having some utility function and that describes how happy the agent is as a numerical function. Most of general equilibrium theory is done with a more general concept known as a preference. And what's significant here is that we allow very general externalities. So the script P is the set of preferences over a single agent's own consumption. So it's how I feel about the stuff I directly consume. But it depends on the consumption of all the other agents. So the curly A is the consumption that everybody else makes. And Y is the production of all commodities. So I might have a different preference if there's a lot of CO2 emitted than I do if not much is emitted. So, for example, if I'm thinking about a house in Minneapolis and one in Miami, then my preferences, my choice between those two might well depend on how much CO2 is emitted in the next 10 years. With the more CO2 being emitted, the better the Minneapolis house looks and the worse the Miami house looks. And we also allow preferences to depend on prices. So they depend on a lot of things they're not allowed to depend on in the standard forms of general equilibrium. There are models that deal with these kinds of externalities, so that part is not new. We are taking existing formulations here, but it's not the sort of standard basic formulation that you see either in the Air-de-Brim model or that's the focus of the general equilibrium portion of graduate micro. Each agent has an initial endowment, so these are commodities, which might be actually commodities that are useful to consume directly, but it might also be labor. So it might be that the agent supplies labor to firms, draws wages, and use that to finance consumption. Okay, now I said that there are firms, so firms have to have shareholders. There has to be somebody who gets the profit or absorbs the loss of the firm's operation. So the shareholdings of the firms, they're held by the individual consumers and they have to add up to one. So there's one share issued and individuals have fractions. So we do restrict shareholdings to be non-negative. So we're not allowing short sales. That's not really terribly important here. There's a kind of nagging issue in general equilibrium theory that concerns what's called the survival assumption. So the issue is if a person is supplying labor but starves to death first, and so can't supply the labor, then that's unfortunate for starters, but it's also, it messes up the equilibrium. So if I forget about, my ethical and philosophical views and just ask about the model, well, it messes up the model. So we want to impose something to make the model coherent, and we want to ensure that individuals can survive. And the survival gets much messier if you allow negative shareholdings, because somebody could be in a very deep hole in the beginning. They have negative shareholdings of the firms and they owe so much money that they can't ever begin to cover their debt and to buy food. So it makes it a little bit easier. Okay, so the government, as I've said, chooses to regulate the first K commodities. And for each of those, it assigns a quota to each of the firms. Okay, including the government firm. Okay, so we said the government firm was a dummy. It can't actually do anything. What it can do, however, if it's given a quota to begin with, then it can generate revenue from lending out or selling that quota. Okay, so M is the sum of the MJs. MJ is the negative of the quota assigned to firm J, including the government, and M is the sum of those things. And our quota compliance region is going to require, what this is saying in terms of words is the total amount of emissions of regulated commodities will be exactly the vector minus M. And for the other commodities, the non-regulated ones, we're going to have a region where the outcome, equilibrium outcome, is going to belong. And that could either be zero, so it's supply equals demand, or it could be the whole set of negative vectors. Okay. So I want to begin with an example that looks at property rights. And part of the reason this is important is that, as Nick observed, and as a lot of people have argued, quotas and taxes seem like the same thing. But there's nonetheless been an active discussion in the literature about whether quotas or taxes are a better method for dealing with carbon dioxide regulation. And part of that has focused on the fact that with cap and trade, all of the quota is being given to the individual firms. And getting quota to emit for free. I mean, so typically it might be, last year's emissions times 0.85 or 0.9. So you have to gradually ratchet them down, but your right to emit is based on your historical emissions. Well, that quota that's assigned to the firms is immensely valuable. And that value, in effect, passes through to the shareholders. So part of the reason people have favored taxes is that the tax goes to the government and then can be rebated to individuals in whatever way the government chooses. It could be rebated equally. So if you buy electricity in California from PG&E twice a year, you get, I think it's an equal share per household of the benefits of the carbon tax. So it's a very modest amount. The carbon tax in California is quite low. But you could do it equally in the population, or you could give it more to people of lower income, or you could use it to fund other programs. But the tax is something that potentially can be progressive or provide equal benefits to all income groups. Whereas the property rights inherent in cap and trade really flow to the firms, and from the firms, they flow to the shareholders of the firms, who happen to be people who are wealthier. So that's part of the argument in the literature about why taxes may be better than cap and trade or quotas. In our model, we're going to see that that first of all, these property rights really do matter. But secondly, by the fact that we have the ability to assign quota to the government firm, we can achieve exactly the same thing as we could in cap and trade. So in a sense, that's the easiest counterexample to the next comment, that taxes and quotas are the same. You need to, in order for that really to be true, you need to be sure that the distributional consequences for consumption by individuals are the same, and it's via assigning a quota to the government firm that we can do that. Yeah.
My question was, who's taxed and who's quota? Like, I should tax companies for emitting, but I can also tax my house for emitting. But doesn't that figure into the discussion of next comment, or the same thing with a quota? I can be given an allowance to drive my combustion engine car.
So yeah, I mean, so where you collect the tax, so if you have multi-country production, and do you have a value added tax, or do you just tax at the end? If in a single country you have a network of supply chains, and where do you impose the tax on that? Those are all valid and important issues, but they're not ones you can address in the general equilibrium framework, because even though within this there are firms making supplies to other firms, which then sell the goods, in the end, the prices are all determined simultaneously. I don't think you can get down to very well to the level of who's actually bearing the burden of the tax. So I think the model is more, for better or worse, more abstract than you really need in order to address that sort of question.
So maybe maybe this is the same question, but just only in the context of companies. But you have the supply chain, just use the phrase. So the healthcare industry, which is not often tagged as a big polluter, in fact, has these giant cement buildings, does other things that might, if you look at a supply chain version of who's emitting carbon, it might be more them than, say, ExxonMobil or somebody else. Is that taken account of in your theory?
Well, the way it would be accounted for is if they build a building with concrete, and CO2 was emitted as part of the production of that concrete, which it typically is, although I think there are methods of producing concrete that are less carbon intensive, but at the point at which the concrete was produced, the CO2 emission at that point was taxed. And then that would flow through into the costs of the healthcare company, which then might be passed on to their consumers or might be borne by the shareholders or somewhere in between. But you're unlikely in a general equilibrium framework to be able to say cleanly who it is who ends up worse off as a result of that tax.
That most of the very simplistic emissions calculations that I see don't attribute much
Right.
to those that use stuff like cement, but attributes instead to the wood burning utility.
Well,
Somebody else.
so a carbon tax, as discussed here, is a tax when the emission occurs. So if it's steel making, it's paid at the time the steel is made and the emission occurs.
Well, this is very much at odds with the way ESG funds are created these days, which is probably good. But
Well, we're not trying to identify who's a good firm and who's a bad firm. We're trying to regulate carbon emissions, so it's a different objective.
I don't necessarily think so. I think the people who are investing that way.
Okay, they may be trying to do that, but we're looking at this from the standpoint of government, and it's got some policy levers. One of which is imposing quotas, the other one is imposing taxes, and we're trying to say what the effects of doing that are. Okay.
Could you, I'm sorry, I'm being slow here. Could you say a little more about the function of the government firm's quota and how that affects the private firm's quotas?
So each firm gets a quota, and it could be that all of it goes to the government firm.
Yeah.
Or it could be that all of it goes to the private firms or somewhere in between. So let's say I'm a steel company. So I've got a quota on my emissions. Do I have to operate in such a way that I fall within that quota? The answer is no. So I can emit more, but if I do that, I need to have somebody else emit less than their quota. And although, so at equilibrium, the total amounts of emissions are equal to the total amount of quota that was allocated. And if I emit less than my quota allows, then in effect that allows me to sell that right to another firm.
Yeah, that's cap and trade, I guess.
That's correct. That's the trade part of cap and trade.
Right.
And in a general equilibrium model where each firm gets a quota, that trade occurs in the sense that the equilibrium price will end up taking it into account. So there are no explicit payments between companies in our model, but nonetheless, it works exactly the same way as cap and trade. There will be, once I've established the quota, there will be a price of emissions. And if I end up using less than my quota, then I get income derived from the difference between what I actually emitted and what my quota was. And that money comes from the Valrasian auctioneer, not explicitly as a payment from another company.
Could that come from the government, or if the government can have a quota, or could you buy quota from the government if you need it?
So at equilibrium, everyone's emissions sum up to the quota. And as a consequence of that, there will be a typically negative price at equilibrium on emissions And the government, which emits nothing but has this quota, ends up generating revenue from that. So in effect, you buy quota from the government, but that works through the supply and demand determination of price in the model. It doesn't come from an explicit transaction that this firm pays specific dollars to the government for the specific quota right.
I mean, is it all resolved in an auction? Is that the model?
It's all resolved by the Volrasian auctioneer.
Okay. Thank you.
Okay. So the Volrasian auctioneer is a fiction who announces prices for the goods, and then firms and consumers say what they would like to buy or sell, and then the Volrasian auctioneer adjusts the prices until equilibrium is reached. So exactly who is paying what money to whom is something that's not very clear in the model. It's sort of like everybody comes to the Volrasian auctioneer and deposits cash to take goods, or they deposit goods to take cash, or some combination of them.
Thank you.
Okay, so the shareholdings of the individual firms are exogenously specified in this model, just as in Pierre de Breu model. The government determines the shareholdings of the government firm. So again, this could be equal shares for all people or equal shares for all households. That's a choice, and it's an important choice. So the government makes two important choices. One is, well, actually three: how much pollution to allow, so what the total quota is, how to allocate that between itself and the private firms, and how to allocate the revenue the government generates from the government firm not using its quota. Okay, I'm wanting to move ahead a little bit. So I want to, rather than go through, well, let me think whether I want to go through this in detail. Yeah, maybe I should, because it also sets up the framework for the examples that follow. So this is an example on quota property rights. So there are three commodities: CO2, coal, and electricity. Okay, so the technology is you can burn coal and you generate electricity and you generate CO2 emission as a byproduct. Okay, and there are two agents who are identical in all but one respect. So the first thing, the consumption, basically that just says they can't consume CO2. So CO2 goes into the atmosphere and has bad effects on me, on everyone. But I can't consume it. I can't breathe it in and make it go away. It's just out there in the atmosphere. And then they're allowed to consume a non-negative amount of coal and electricity. Each one is endowed initially with 1 unit of coal, so that the distribution of the basic commodities in the society is absolutely equal. And they also have the same preference. It's a utility function. Utility of the agent is just the agent's electricity consumption minus the externality, which is based on the total amount of CO2 emissions. So minus V squared over 2, where V is the amount of emissions. Okay, I'll say in a minute how these differ, but the two consumers so far are absolutely identical.
Why is there a V there instead of one of those C1, C2, and C3?
Okay, so so the individuals are not actually consuming CO2. CO2 is the V is the total amount of CO2 released. So that's going to be the total amount that's produced in the generation of electricity, which is just the amount of electricity in this example. Okay. And there's no technology in here to get rid of CO2. So in effect, it's going to be agent one's consumption of electricity plus agent two's consumption of electricity. So it's the C3 from agent one plus the C3 from agent two.
Why does it get squared?
Because the bad consequences of carbon emissions get worse as you emit more of it.
But I couldn't.
Well, fine. This is an example.
Oh, okay. This is just a choice you made.
This is an example.
That allowed that, you know.
The relevant thing is that you've got increasing marginal disutility of CO2 emissions, which I think is the right model. Okay. Let's skip that bullet. Let's go to this one. So the agents, what this says is the agents have equal shares in the government firm. So any profit the government firm generates will be equally divided between them. But the first agent owns the firm and the second agent doesn't have any shares in the firm. And now we're going to look at two situations. So the first is that, the first is the government decides how much emissions to allow. So it chooses an M. That's the negative of the total amount of emissions that will be allowed. And it has two choices. It can allocate that quota to the government firm or to the private firm. And in this example, how that quota is allocated makes no difference in the amount of CO2 emitted. It makes no difference in the prices at equilibrium. Okay, if I set a quota of M, then the total amount of CO2 that's emitted is M, and the equilibrium price in both cases. And the equilibrium price in both cases is the same. Coal is worth zero. The price of CO2 emissions is minus a half. The price of electricity is a half. So the two equilibria look identical at the whole economy level. However, they're very different in the consumptions of the individual agents. If I allocate the quota to the government firm, both agents consume half of the electricity that's produced. And if I allocate the quota to the private firm, then the first agent consumes all of the electricity and the second agent consumes zero. So these individuals are identical except in their shareholdings. The equilibrium prices and productions are identical in the two situations, but the distribution of consumption between the two agents is radically different. And this is true even though the second agent is endowed with coal. Okay, so you would think that the agent would get some value out of selling coal and would get a little bit of electricity generated from it. But in fact, in this example, the equilibrium price of coal is zero. And the reason for that is the quota doesn't allow all of the coal to be used. Okay, we restrict the amount of electricity, we restrict the amount of CO2 that can be emitted. That puts a limit, given the technology, on the amount of coal that can be used. And there's some coal left over. And therefore, the equilibrium price of it is zero. So,
in other words, there's some useless coal at equilibrium.
Right.
Coal no one can use, so no one will pay for it.
It's a stranded asset.
Mm-hmm.
Yeah. Okay. So this is mathematics that's needed to specify the model formally. I'm going to talk about it quickly and in words. So we have to first of all given a production vector is y, so this is specifying the productions of each of the firms, and given a price vector p, then I have to figure out how much income each of the individuals has, and I have to figure out what the firms do. So let's start with the firms. The firms maximize profit. And I think a note is that the quota that the firm is assigned may generate profit, but it doesn't affect the profit maximizing decision. It's a fixed quantity. Okay, the firm's profit is P dot by J plus the projection of the price vector P onto the regulated quantities times the quota that the firm has. So if you're given quota, that gives you a constant addition to your firm's profit, but it's a constant, and therefore the choice of production level that maximizes profit is not affected by the quota you're assigned to. So firms do exactly the same thing, independent of what the quota is. Okay, their supply is just the usual general equilibrium supply to maximize profit given their production set. What do the individuals do? Well, they have a certain amount of income to spend, and it comes from selling their endowment, and it comes from the dividends that they get from the firms, and it comes from the share of the profit of the government firm. So these are dividends paid by the firms, including the government firm. So your share of the profits of the government firm, add to your budget, and then your demand set is just a set of all things that are affordable, such that there's nothing better that's also affordable. So that's standard general equilibrium. Okay, so I'm looking at the time and I want to go to this theorem, which says under moderate regularity conditions. Let's say a little bit about what that means. Every finite economy, production economy with a feasible quota minus M has a quota equilibrium. Okay, so first of all, what do I mean by a feasible quota? Well, I might specify a very large quota on emissions. And there's actually no technology that actually will produce that much emissions. And our notion of equilibrium requires the emissions be exactly equal to the quota. So it might be infeasible. There's no way of organizing production and consumption in order to get up to that large a level. But if there is at least one choice of productions by the firm that ends up producing that level of emissions, then there is a quota equilibrium. What do moderate regularity conditions mean? Well, I've got that on a slide at the end of the talk so that you can look in the slides after the talk and see it. Basically, these are standard conditions from general equilibrium. And I mentioned earlier this annoying issue about survival. And so we have to deal with that. The survival thing is the part that's not really very satisfactory about that. The rest of it is very standard GE. Now, the best previous theorem on this is in a book by Florenzano, and she proved a special case of this, but her quota compliance, her compliance region is a cone. So that says you can require supply equals demand for some commodities and allow supply to be greater than demand for other commodities, but it doesn't provide a way to say the supply minus the demand must be exactly equal to this. So it doesn't allow you to say, sorry, let's put it this way. It allows you to say you can't emit CO2. It allows you to say you can have unlimited emissions of CO2, but it doesn't allow you to say that CO2 emissions must be exactly a gigaton. And in terms of proving this, we, to a large extent, use Florenzano's proof, but show that by introducing the quotas into the firms and into the government, we can turn our equilibrium with quotas into one that satisfies her assumptions. So it's the same proof, but a different application in essence. Okay, I want to talk about the constrained Pareto optimality. So what's true about the first welfare theorem in our setting? Okay, so there's no hope that quota equilibria are full Pareto optimal. So remember, full Pareto optimal would mean there's no other way of organizing society that makes everybody better off. And the thing is that there is an equilibrium with zero quotas for which you return immediately to a pre-industrial society, which is a very bad outcome. There's also an equilibrium where the quota is very large and then there's no constraint on carbon emissions and the world, effectively comes to an end in a few hundred years because the planet becomes too hot to sustain life. So the right outcome is somewhere in between, and all of these things are quota equilibria. Quota equilibrium can do nothing to address climate change. It can do too much to address climate change. Somewhere in between is, where you want to end up being, but you can't say that that a quota equilibrium is necessarily good. It could be very bad, but you would hope that at least one of them is good. Okay, now I'm going to make an assumption to restrict the externalities. So basically, this is saying that the externality arises solely from the total amount of emissions of the first K commodity. So if we're only worried about CO2, then my preferences are affected by the total amount of CO2 released, but not by the prices directly, not by other people's consumption. It's only the effect of global warming that alters my preference. And we say that two feasible consumption production pairs that have the same total net pollution emissions, we say that, sorry, let me do it this way. Basically, it's constrained Pareto optimal if there's no feasible consumption production pair with the same emissions that makes everybody better off. Okay, so again, if the only thing that affects your welfare is your own consumption and the total CO2 emission, then constrained Pareto optimal means that there's no way with the same total emissions to make everybody better off. And this is the version of the first welfare theorem. Again, suppose that the only externality arises from total net emissions under the same moderate conditions. If we have a quota equilibrium, then it's constrained Pareto optimal. There's no way to organize a society and produce the same emissions to make everyone better off. So, the relevance of that for government policy has to do with how closely you regulate the actions of firms. Now, there's an assumption here, which is that firms are price takers. And so we've ruled out in the formulation market power that comes from having a large market share or monopoly power. So that's a very, very significant limitation. But the story is that, if you're focusing on controlling CO2 emissions, then rather than trying to directly regulate at a factory level or a firm level each emission, you're likely to be better off by setting the quota and then letting the market determine what the outcome is. And this is a story that's, again, embedded in the literature about both cap and trade and carbon taxes. So it's most clearly stated in terms of cap and trade. The idea in cap and trade is it achieves the reduction you want, and it does so in the most efficient way because firms for whom it's inexpensive to reduce their CO2 emissions will do so, and those CO2 emissions will then be in effect transferred to the firms for whom it's more expensive. Whereas if you regulate at an individual firm or factory level what the emissions are going to be, then it's likely that you're going to be worse off than you could be because you're not focusing on doing the easiest things to reduce emissions. You're doing a bunch of hard things along with the easy things. So this version of the first welfare theorem is a precise statement of the somewhat vague argument that's been made in cap and trade that it's an efficient way to achieve the desired reductions. Okay. Production economy with tax. I'm not going to have a lot of time to talk about this, but let me hit the highlights. So here now there are no quotas. Okay. What the government does is it tells the Valrasian auctioneer that the price of these regulated goods must be specified as follows, and then tells the Valrasian auctioneer to go ahead and try to find a price for the other goods that clears markets. Okay, so there's no limit on emissions in principle, but if you emit, you're going to pay a tax for it, and that tax will induce people to emit less. So we've got, a notion of equilibrium is going to be supply equals demand. So we have to figure out what the budget and demand sets are of individuals. And we can talk about a notion of a tax equilibrium. And the key elements are the equilibrium price factor of the regulated commodities is what the government specified in the beginning. Everyone's consumption is in their demand set, so it optimizes the value of their consumption given their budget set, and firms are maximizing profit. And the total emissions are in this set V. So V in principle will allow arbitrarily large CO2 emissions, but in practice, the equilibrium won't do that because the price will constrain it. So, two questions. First, does tax equilibrium exist in general? No, that's not true. What's the connection between tax and quota equilibrium? So this is Nick's question at the beginning, and it's also an assertion in Bill Nordhaus's book, that basically these are the same thing. We want to try to formulate that. And how does tax equilibrium compare to quota equilibrium in terms of its ability to achieve a particular outcome? So Bill Nordhaus and Nick are correct. There is a precise statement saying every quota equilibrium is a tax equilibrium and vice versa, but we need to be a little bit careful with the statement. So if I start with a quota equilibrium, so again, this could allow me to give the quota to the government firm or to the private firms or some combination, doesn't matter. Start with any quota equilibrium, then look at the consumptions and look at the productions and look at the prices. Those are things you normally think about as characterizing an equilibrium. There's a tax equilibrium of a production economy, and the tax rate for the regulated goods is just the goods specified at the prices specified at the quota equilibrium. And you need to say how the revenues from the tax are going to be distributed, and you distribute them in exactly the way they got distributed at the quota equilibrium. So this might not be a very equitable distribution of income. If we started off with a cap and trade where all of the quotas assigned to private firms, that's going to be very good for rich people, and this formula preserves that benefit for rich people. Okay, and on the other hand, if I start with a tax equilibrium, so these are consumptions by agents, productions by firms, price factor, then in fact, it's a quota equilibrium where the global quota is the total amount of emissions that were produced in the tax equilibrium. Okay, and each private firm's quota is zero. So global quota equilibrium just means all of the quotas assigned to the government firm, not the private firms. So where does this get tricky? So one thing is I've alluded a couple of times to the fact that tax equilibrium need not exist. And there's also a difficulty in using tax equilibrium to get a specific outcome. And that's sort of hidden in these statements. And the reason it's hidden is that it could well be a multiplicity of tax equilibrium. So first of all, if I specify tax rate, there might be no equilibrium. But in some sense, worse is that if I specify a tax rate, there might be a whole lot of equilibrium. And so in this theorem, if I start off with a quota equilibrium, then I can achieve the same production and consumption as a tax equilibrium. But if I specify that tax, I might also get something completely different. Okay, so there may be a whole lot of tax equilibrium consistent with this tax rate that achieve very different production and outcomes, different CO2 emissions. Inherently, in examples at least, the tax equilibrium is not very good at actually achieving a specified level of reduction of CO2 emissions. And I think I will finish with this example that makes that point. So this is like the previous example we had earlier. We said about three commodities: CO2, coal, and electricity. And here there's only one agent. So having a single agent helps you to make sharp notions of what's the best outcome, what's the optimal outcome. If you have multiple agents, then the best outcome the set of Pareto optimal outcomes might be relatively large. With a single agent, it's likely to be a single point or at least a small set. So there's a single agent, and the single agent can't consume CO2. She can consume coal and electricity. She is endowed with 1 unit of coal, and we have the same utility function as before at C3. So you get 1 unit of utility for each unit of electricity minus the square of the total emissions. What's the wrinkle compared with the previous one? So the wrinkle is we've got now two firms and two technologies. So the first firm burns coal, burns 1 unit of coal, produces 1 unit of electricity, and 1 unit of CO2 as a byproduct. And the second firm sequesters CO2. So this is a technology which is actually being implemented on an experimental basis. There remain considerable doubts about whether it's actually a viable solution to generating electricity from burning fossil fuels and sequestering the resulting CO2. But it's going to illustrate our point about the multiplicity of tax equilibrium. And it's also a technology that might, in fact, become significant in the future and is currently being implemented on an experimental basis. So what does this firm do? The firm can take 1 unit of electricity and get rid of 2 units of CO2. Okay. So this is what the tax equilibrium look like. So look, first of all, on this panel on the left. So on the x-axis, we have the tax rate, and on the y-axis, we have the CO2 emissions at equilibrium. And what the picture shows is that if the tax rate's less than a quarter, then CO2 emissions are 1. So basically, all of the coal is burned and no CO2 is sequestered. Okay. And if the tax is greater than a quarter, I want you to notice that along the x-axis to the right of a quarter, it's black and not blue. Okay. It's not that for a tax rate greater than a quarter, the CO2 emissions are 0, which is what we would hope for. But in fact, there's no equilibrium. So if you try to set the tax rate greater than a quarter, there's no equilibrium. And if you set the tax rate equal to a quarter, then the CO2 emissions can be anything between 0 and 1. And the reason for this is the linear technology for sequestration. Actually, we also have linear technology for electricity production. So when you set the tax rate equal to a quarter, the firms are essentially indifferent among what scale to operate. They can use up all of the coal or not, and they can sequester all of the CO2 or not. The equilibrium is not, you got multiple equilibrium, it doesn't nail down what the outcome is. In this picture, we're showing the set of possible equilibrium outcomes with a tax rate of a quarter. And when the tax rate is less than a quarter, you just have that dot up the upper right at 1,1. When the tax rate equals a quarter, equilibrium can be anything along the diagonal blue line. So anywhere from no sequestration and consuming 1 unit of electricity and 1 unit of CO2 being released to consuming a half unit of electricity and no CO2 emissions because they've been dealt with by sequestration. So suppose your goal is to have CO2 emissions be no more than a half or equal to a half. Well, if you set the tax rate equals a quarter, you have no control over it. The equilibrium could be anything along this line. It could be you've got 1 unit of CO2 emission. It could be you've got 0 units. The tax rate a quarter doesn't effectively limit the emissions in the equilibrium because of the multiplicity of equilibrium. Quota equilibrium can get you whatever you want. It turns out that for this specification of the model, the optimal level is electricity consumption of 5/8 and CO2 emissions positive but relatively small. It's some point in the middle, and quota equilibrium can get you there, but in this example, tax equilibrium can't. There's no guarantee that you get the right point on this line. So where are we going with this? Well, We have another example where the technology for sequestration is nonlinear, and there the taxes work better. But getting a general formulation in which you can prove that tax equilibria can get whatever you want is something that's pretty challenging. We're not sure that it's even possible to produce a clean theorem like that. Let me flip through to the conclusion. Okay, so we're going to take these regulatory mechanisms and incorporate them into the baseline model of perfect competition in microeconomics, the Berkeley model. Okay, and under moderate conditions, quota equilibrium exists, and it's constrained Pareto Optimal has a nice welfare property that justifies the argument for cap and trade. Often, so there's not a general theorem, but it's true in examples, and we think it's a general phenomenon that you can get full Pareto optimality of the quota equilibrium by choosing the right quota. Property rights matter a huge amount. Every quota equilibrium can be realized as a tax equilibrium and vice versa. But because of the potential multiplicity of tax equilibrium, you can't guarantee you'll get the particular emissions level that you wanted. Okay, tax equilibrium may not exist for certain tax rates. And we have an example that is a little bit more positive in terms of what you can do with taxes. In terms of future work, I want to highlight just one of these bullets and allow the hungry hordes outside to come in. The Berkeley model is supposedly allowing multiple periods, but it doesn't really, because the market meets only once, and you can think about writing contracts of future consumption, but those don't. It's not a very plausible model of that. But we could do a multi-period model, and in that model, you could do things like allow for futures contracts for emission rights. And there's potentially a substantial payoff for doing that in terms of real policy, because one of the drawbacks in the improvement of technology to reduce CO2 emissions is that it requires a big investment. And you may not know in advance what the future price of CO2 emissions will be. So whether you can go to the bank and borrow money or whether you can justify the investment today, you can't do that readily without knowing what the future prices will be. If you had futures markets for emissions prices, then a firm could offset the risk that those future emission prices will vary through also trading a futures contract. So there's a potential for this to improve the financing of decisions by utilities in terms of what technology to use to generate electricity and so forth. And there are a bunch of other things, but I think time's up, so I should stop.
Sort of one quick comment. The theorems that you mentioned from Mr. Nordstrom are far more.
Nick, we're going to need to take the questions offline. I'm sorry, we've lost our rights to the room, but please do email that question or call us up, or even better, come on down.
Yeah, okay.
I'd like to thank our speaker, clever about future works and then a specific topic. And that next week, Alec Kirschwall will be joining us from University of Florida, Florida State, Tallahassee, and he'll be here in person. We'll also be available online and hope to see many of you then. Bob, are you going to post slides?
Yes.
Recordings?
Yes, please.
Take questions by email.
Sure.
And all that stuff. Thanks, everyone. Sorry about that, Nick. Down.
Sure. Thank you. Bye-bye.
That's fine. Yeah, you get it.